All right, so we're going to talk about relativity. Now, before we get into the specifics of the theory of relativity, it's important to understand the idea of relative velocity. Velocity is a fancy word for speed. So let's say this is you, and you're standing in front of your beautiful greenhouse, waiting for your friend to drive up. You're expecting him any moment. And he is going to drive up in his flashy new orange sports car. Now he's driving at 40 miles an hour. There it is. And there he is. So he's moving to the left at 40 miles an hour. I'm going to show it like this with an arrow and the number. Now I'm drawing it in green because this is the speed that you see him moving to the left at. You see him moving to the left at 40 miles an hour. Now from his perspective, he sees you moving to the right at 40 miles an hour. So all the objects, if he looks out his window, he sees them move to the right because he is in his car, which is driving off to the left. Now, that's relative velocity. So from his perspective, he sees other things moving relative to him, and from your perspective, you see him moving relative to you. Let's add another perspective. Your mom is driving from the other direction. Now, she's a much safer driver, so she'll only be going 20 miles per hour, and she also drives a safe, boxy car. So here is your mom driving to the right with her hair hanging out the window. Let's see. So she's driving to the right, and that's going to be from your perspective, so I better draw that in green. Your perspective to the right at 20 miles per hour. Now, from her perspective, you are moving to the left outside her window at 20 miles per hour. Straightforward enough. But what about your friend here? He's driving to the left at 40, and she's driving to the right at 20, which means that outside her window, she'll actually see your friend go by at 60 miles an hour, 40 plus 20. 60 miles per hour. And the same is true for your friend. He is going to see your mom driving to the right at that same number of 60 miles per hour. All right, so here's everybody's relative velocities. Let's throw in one more object. And actually, your friend is going to be the one throwing it because, crazy as he is, he decided to throw a baseball outside his car. Throw it straight ahead. There it is, zooming along. And it just happens to be bigger than his head. But he's throwing it at 30 miles per hour. Oops, I should have drawn that in orange. Because from his perspective, he's thrown his baseball at 30 miles per hour. Now, from your perspective, he threw it at 30, but he's also driving at 40. So from the green arrow should show a speed of 70 miles per hour because those speeds will add. Now, what about your mom? She sees yet another speed. From her perspective, this ball is zooming along at 20 plus 40 plus 30. It's actually 90 miles an hour. So as far as she's concerned, your friend is ready for the big leagues with a 90-mile-an-hour fastball. So here we have 3 perspectives on 4 objects. We could even put in the perspective of the baseball. From the baseball's perspective, what are all of the relative velocities here? Your friend threw the ball to the left at 30 miles an hour. So from the ball's perspective, you can imagine maybe a flea or an ant on the ball. Your friend is going to be moving to the right at 30 miles per hour because it's going away from him. Think about it from even in a regular baseball game, when the pitcher throws the ball, if we had a camera on the ball, we'd see the pitcher get further away from the ball after it was thrown. Now, what about Mom over here? The ball is approaching Mom. It is just going to be the same number but in the opposite direction. The ball, from the ball's perspective, this car is approaching at 90 miles per hour. And then finally, this is going to be mirrored here. So there's a mirror. We've already noticed that. The relative velocity between these two cars is 60 miles an hour. And so those same numbers appear in both places and the arrows are reversed. So from the ball's perspective, you are going to be moving to the right at 70 miles per hour. Again, if we had a camera on the ball, you'd see that you standing in front of your house zoom past to the right. So here we have a really nice example of relative velocity. There's 4 different objects or people, observers, that are moving relative to each other. And so it is the relative velocities that are important here. Each measures a different velocity because they're moving relative to each other. So now, how does this connect to the theory of relativity? Just before the 20th century, science experiments were showing some kind of strange things with the speed of light. And Albert Einstein took the scientific evidence from the time and built a whole theory around the idea that the speed of light is the same for all observers. That's like saying that there's an object, like this baseball, for example, that no matter who is looking at it and how fast they're moving, everybody measures the same speed for that object. So for the theory of relativity, that's the speed of light. And it's going to be a constant, and it's usually represented by the letter c. C for constant is the speed of light. So in the next video, we will talk about what the implications are of the speed of light being the same for all observers. Because if everybody has to measure that speed to be the same, it actually does some pretty interesting things to distance and time.